angle whose vertex is the center of the circle. For example, if I draw a circle, let's call it circle A central angle would be an angle where the vertex is at the center. So I can draw out line segments from A, and this angle, let's say theta, is an example of a central angle. It's at the center of my circle. An arc is the unbroken part of the circle consisting of 2 points called endpoints and all the points between them. For example, once again I will draw a circle. Let's draw circle A. And my arc is if I were to choose 2 points, 2 endpoints on my circle, B and C, and I can go ahead and connect those 2 points. That forms an arc. There are a couple different types of arcs that we'll talk about that are on my next slide, so if you haven't gotten these 2 definitions, go ahead and pause this video and write those down. 2 different types of arcs are minor arcs and major arcs. The main difference is minor arcs are smaller than major arcs. In fact, minor arcs measure less than 180 degrees, and major arcs measure greater than 180 degrees. I'm going to go ahead and draw my picture for you first over in the diagram. So once again, if I have a circle, we're going to call this circle B. A minor arc would be an arc that is located on the side here. Here's my minor arc. I'm going to call this arc AC. And in order to find the measure of this arc, I'm going to connect my endpoints to the center of the circle. And once I've connected those endpoints of my arc, if I find the measure of this central angle, that's going to be the same measure as my arc. So the measure of a minor arc will always equal the measure of the central angle. In this case, the measure of arc AC, and I represent arc by putting not a line like we do segments, but an actual arc over the letters AC, it will equal X. My major arc, on the other hand, is, I'm going to draw the exact same picture. Here's circle B. And I'm going to go ahead and draw those same 2 endpoints. Here's A and here's C. Except when I'm talking about a major arc, I want everything in the opposite direction. So here's an example of a major arc. It's a little bit larger. But in order to name this major arc, I need to throw in 1 more point so that I know I'm talking about the opposite direction. So that major arc is going to intersect at some point D. Well, in order to find the measure of this arc, if a circle measures 360 degrees, I'm going to take 360, and I want that whole circle except the measure of arc AC. So I'm going to go ahead and subtract the central angle. 360 degrees minus that central angle, since that central angle represents the measure of arc AC. So my formula for the measure of arc ABC would be 360 minus X. If, once again, I draw in the fact that whatever this central angle is, it measures X degrees. Your last arc is a special arc, and we call this the semicircle. It's an arc whose endpoints lie on the diameter. It will always equal 108 degrees. It is half my circle. And to draw a semicircle, again, start with a circle, and its endpoints lie on the diameter. Well, from 11.1, we know the diameter cuts through the middle of the circle. So here's my middle, once again at B. And I'm going to go ahead and call my diameter AC. Here are those endpoints, AC. The semicircle is that arc that connects A and C. It connects those endpoints of the diameter. Half my circle equals 180 degrees. Now, one thing to help us in knowing the difference between minor and major arcs minor arcs are always named by 2 points. And as we could tell in my first example, AC just had 2 points. Whereas major arcs and semicircles are named by 3 points, larger arcs. Once again, I'm going to move to the next slide, so pause the video if you haven't gotten all of this down. Our next vocabulary is adjacent arcs, and adjacent means to be right next to. So adjacent arcs are arcs that are in the same circle that intersect at exactly 1 point. So for example, I've got some circle here, and I have 2 arcs. I have arc AB, and I have arc BC, and they share that point BC. So if I want to find the measure of an arc that's formed by these 2 adjacent arcs, all I need to do is take the sum of the measures of the 2 arcs, of those 2 adjacent arcs. So with respect to this picture, the measure of arc AC will equal the measure of arc AB plus the measure of arc BC, because they share that common endpoint of B. Similar to how we did segment addition back in chapter 1. Now let's try an example with this. If I want to find the measure of arc BD, well, remember the measure of arcs always equal the central angle from where they come from, so I want to find the measure of this angle right here. Well, neither of those are labeled, but the other 2 are, which help us. And one thing that we can tell is that AC is a diameter, which means it will always form this arc, this semicircle, which will total 180 degrees. So let's first start by finding this piece right here. Well, if that arc is 180, to find that measure, I'm going to take 180 minus 97.4 minus 52, and all we're left with is 30.6. That means this angle here is 30.6 degrees. In the same fashion, we're going to go ahead and find this other missing piece. Well, this comes from the semicircle BE, and same thing, it's got to equal 180 degrees. So I'm going to go ahead and subtract those 2 angles, 50 and 30.6, and all we're left with is 97.4. Therefore, this entire arc BD will be the sum of 97.4 and 30.6. And that is the measure of my arc BD. And to clue us in on why we're measuring this side of BD is because I only have 2 letters, so it has to be that minor arc. It's going to be the smaller one, not the one on the opposite side here. Okay, we're going to skip number 2 and head on to our next definition here. I can have congruent arcs if I've got some circle and I know that the 2 arcs have the same measure. Congruent arcs will always have the same measure. Within a circle, congruent arcs are 2 arcs that have the same measure. For example, since those central angles are both x degrees, whatever x is, they're the same value, then ST is congruent to arc UV. Going off of this, we sort of have a flow of 3 theorems and a circle or congruent circles. Congruent central angles, so if angle EAD is congruent to angle CAD, then they will have congruent chords. So if those 2 angles are congruent, that means that chord DE would have to be congruent to chord BC. Similar is number 2. If I know I have congruent chords, so in our picture ED is given to me to be congruent as CB, then I know I'm going to have congruent arcs. So therefore arc ED is congruent to arc CB. And make sure you've notated arcs and chords in the opposite. One's at a straight line, the other is curved. If I'm told that I have congruent arcs, so in my picture this time I know arc EG is congruent to arc CB, then I know that I have congruent central angles. So therefore, angle DAE would have to be congruent to angle BAC. Okay, moving on to our next example. In the picture, I have two congruent chords. TV is congruent to WS. Well, from our last slide, congruent chords will always yield congruent arcs. So therefore, arc TV will have to be congruent to arc SW. I have two equations, so let's go ahead and set those equal to each other. 9n minus 11 equals 7n plus 11. Go ahead and subtract your 7n to the left, add your 11 to the right, and divide. We get n equaling 11. The question asks for finding the measure of arc WS, which has that equation 7n plus 11. So now all I have to do is plug in my n value, which we found to be 11, into our equation 7n plus 11. And we get the measure of arc WS to be 88 degrees. Pause this video if you haven't gotten this all the way down, and we have two more theorems left. 11-2-3 states that in a circle, if the radius or diameter is perpendicular to a chord, then it must bisect the chord and the arc as well. For example, if I have some circle and it says if the radius for a chord, I'm going to go with radius, is perpendicular, so here's my radius, we'll call it CD. If it happens to be perpendicular to a chord, let's throw in chord EF. The chord connects two endpoints on a circle. If this radius is perpendicular to that chord, so that's your hypothesis, the fact that CD is perpendicular to EF, then my conclusion will be that CD must bisect EF and EF as an arc, both the chord and the arc. 11-2-4 is just the converse. So in a circle, the perpendicular bisector of chord is a radius or diameter. So for this picture, I know that I have a perpendicular bisector of a chord. So I'm going to have that same chord, we'll call it EF, and I have a perpendicular bisector. So it's cutting this chord in half at a right angle, and that is the given information. We'll call this piece AK. So the hypothesis or the given is that this segment is perpendicularly bisecting chord EF. Therefore, my conclusion will state that JK must then be a radius of circle A. I'm sorry, I did not use J. I used A. We'll call this AK. AK is a radius of circle A. And that is your mass theorem for 11.2. We will use these concepts tomorrow in class, so make sure you have your notes completed and ready to go.